Yes. So now we want to get to know our first discrete distribution, namely the so-called hypergeometric distribution. And this is the distribution that was very close to our lottery example. And what we're going to do first is look at an example to clarify in which situation we have a hypergeometric distribution. And what we always do is, you might remember this from school. We look at urns and then there are balls in there and they have colors. And then we either draw balls from this urn, replacement or without replacement. And you can already see this is essentially the lottery example, just not with numbers printed on them, but with different colored balls. Okay, so what is our example? Scenario. Imagine you have a container, so an urn, and there are 20 balls in there. And there are two categories of them. There are those that are blue, which are 4, and 16 are red. So you see, this is basically our second important property. How many have a property, for example, to be blue, and how many do not have that? And what we do then is we draw from this urn, and now comes the important word, without replacement. So the hypergeometric distribution is without replacement, 5 balls. That's another number we want to set. So that's our scenario. And our random variable is now number of blue balls in the sample. And we can briefly consider what the values of this random variable might look like. So we're drawing 5 times, which means theoretically there could be 0, 1, 2, 3, 4, or 5 blue balls. But we only have 4. We only have 4 blue balls. That means the value 5 cannot occur, so only the values 1, 2, 3, 4 can occur. And now we want to get to know the probability distribution of situation. We've seen that this is a discrete random variable because it only takes on a finite number of values. And so we want to find the probability that x takes on a certain value. And let's do that as an example. And we are considering the probability for x being 2. And how do we do that? We're considering Laplace's random experiment. Every combination of balls is equally likely. So we need to calculate the number of ways that exactly 2 blue balls can occur. And that is the cardinality. So of this set of the event, x equals 2. And we divide that by all the possibilities. So we need to think about how many ways there are to draw exactly 2 blue balls and how many ways there are in total. Randomly draw 5 balls. Okay, let's first consider omega. It's not that hard. We're actually in the lottery situation. We're drawing a total of 5 balls, and we have 20 balls to choose from. We don't put them back 1,000. And that means omega is exactly the binomial coefficient. 20 choose 5. And now we need to think about what the chances are that we draw exactly 2 blue balls. And it's like this. We need to think about how many combinations there are to draw exactly 2 balls that are blue. And exactly, what do we know then? That we also draw 3 red. And we can also look at that with binomial coefficients, namely as follows. We can say we have 4 blue balls and we need to draw 2 from them. Well, we have 2 out of 4 possibilities, or 4 choose, 2, and then we need to draw 3 balls from the 16 balls, and that gives us all the possibilities for the red ones, which adds up to 5 balls. Exactly. And the product of the 2 is then the number of probabilities of the possibilities. And now we can simply form the quotient, and then we get as a result. You have to do that with the calculator, 0.217. So 21.7. And so you see, we've done that for an example of x equals 2, but you could of course do the same for x equals 3, x equals 4, with a similar approach. We'll also take a look at the general formula right away. Maybe let's take a quick look at the distribution when you do it this way. So we've calculated case 2, and here you can see the other probabilities that sum up to 1. And you can see, if you plot that again, that 1, that's exactly 1. What was the color that there is exactly 1? Blue ball. 2001 is the most likely. Yes, but we really had to consider the whole thing as a quotient of these two terms. And now we want to write that down in general again. So what is the hypergeometric distribution? So we had several parameters. On one hand, we have the total population. So how many balls are there in total? That's big N, sos, eos. And out of those, we have M. So that was our 20. Then M has a certain property, for example, to be blue, which were 4 in our case. And then you take a sample of size, N, which was 5, and all of that without replacing the balls. So we have the random variable representing the number of elements in the sample with the desired property, which in our case was blue. And then we have the formula here, which can be written in general as we have the possibility of drawing k from n, and on top we have x with the property, with the specific property, which was ME. And then we need to take the rest, which is nx from nm balls. And that's exactly what we did. And yes, we just need to calculate that, and then we'll get the result. And we call this x is hypergeometrically distributed, and the probability distribution is hypergeometric. To write it briefly, it is x plus h for hypergeometric with parameters. Now, with this distribution, calculate cases like 2001, needing a calculator for large values, h parameters. The key question is, what is the expected value? And exactly now we can look at this distribution. We can calculate it in individual cases like 2001, for which you need a calculator if you get relatively large values. And the exciting thing now is, or the question is much more, what is the expected value? For example, what is the expected value of this distribution and what is the variance of this distribution? And you can already see, if you have to calculate this by hand, it gets relatively complicated because we've already seen that the individual probabilities are quite complicated to calculate. And then there's the expected value and variance, which makes the whole thing even more complicated. But the nice thing is, there are actually formulas for that. So now we're going to dive into this specifically for the expected value, which is simply this expression here, n times m divided by n. So in our case, if we take our example, 5 times 4 divided by 20. Let's take a look at that. 5 times 4 is 1. Actually, if we take another look at the graph, it's not that surprising, but it's still a nice result. So that means 1 is actually the expected value of this, and there is also a formula for the variance, which is a bit more complicated. You plug it in, and then you'll get a value. We're not going to do that now, you can do it again. I just want to tell you that calculating the variance and the expected value is actually much easier. You can even do that by hand, unlike the individual PIS, meaning the probabilities of x2. You can't really do that by hand, or maybe just barely in this case. Usually you can't really do it by hand. And I've already mentioned the typical example is the lottery example. And now we see the plot for that again. So, what are the values here? Well, n is equal to 49, which is important. M is equal to 6. So those are 6 numbers that have these properties. And we draw 6 numbers. And then you can see here how likely it is to get 0 correct, 1 correct, 2 correct, 3 correct, and so on. And then you could also calculate the expected value here, and you can already see that it will probably be somewhere between 1 and 2. Most of the values are actually 1 and 0. So 0 is actually the most likely outcome, meaning you have 0 correct. I'm sure you thought about that too. Getting 6 correct is a very, very low probability. All right, that was the hypergeometric distribution for 2001. And in the next step, we want to look at what happens when we draw with replacement, meaning the population doesn't change during the draw, and that's the binomial distribution. Until then, take care.